So we've looked at how to solve first order differential equations through various means analytically, and we also looked at how to solve them numerically with Euler's method. And now we're going to turn our focus to applications of first order differential equations to real world problems. And we'll be focusing here on linear mathematical models. So we'll look at linear first order differential equations and how they could be used to model the real world and give us real world results. So we'll start by looking at growth and decay, focusing on exponential growth and decay. So a wide variety of phenomena could be modeled by the simple relation that the rate of change, the first order rate of change of a quantity, is related to how much of that quantity there currently is. And this is summarized by this relation here. dx dt is proportional to x. And we could use an equal sign if we get a constant of proportionality. So this here is the constant of proportionality. It's a parameter in our model in order to fix the relation between the rate of change and the quantity. Solving by using separation of variables, we end up with this general solution right there, where x naught, we used the constant c sub 1 while we were solving, and that parameter, we could rewrite it in the form of x naught if we have that relation there, okay? And that's fixed because if you put t equals 0 in here, you'll get that x at t equals 0 is equal to x naught. So that's how we fix the constant in our model in a general way. Something to note here is for growth, we have that k is positive. Okay, so we don't make an assumption about k being either positive or negative while we're solving this. But if k is strictly greater than 0, then you're going to get exponential growth. For example, for bacterial growth, this would be helpful. And when k is less than 0, you're going to get exponential decay. So that's, for example, in radioactivity, follows this exponential decay law. So let's look at an example. So we have a culture initially has P naught number of bacteria. At t equals 1 hour, okay, so units here are important. The number of bacteria is measured to be 3/2 P naught. Okay, so you start with the initial population of P naught, and after 1 hour, you have 1.5 times that, okay? If the rate of growth is proportional to the number of bacteria, okay, this key here is telling you that it follows this relation. Present at time t, determine the time necessary for the number of bacteria to triple. Okay, so we know the initial population. We know at t equals 0, so where we set our clock to the 0 time. We have a population of P naught. We know after 1 hour, we have a population of 1.5 times that. And we want to know when the population will triple. So one big problem here in this problem is we don't know k. So we're not given k in this problem, the constant of proportionality or the rate of growth parameter in this particular model. But we are told this, and we can solve. Okay, and we have P naught that's given in the problem. Okay, when a problem tells you you have P naught number, it means you could assume you know that value P naught. Okay, and our problem is that we don't know k, but we do know that at t equals 1 hour, we have that the population is 3/2 P naught. So we're going to take advantage of that. We have the general form, and we have the value at a particular point in time. So on the left-hand side here, and separate in your mind between the left-hand side, which is just a condition given in the problem, and the right-hand side, which is plugging in the value 1 into the general form that we have, okay? For basically our equation that we solved. And so combining these two terms, these two relations, we could then solve for k. Okay, you just take the log of both sides after some algebra. Notice something crucial here. I mean, someone would wonder, well, we don't know the initial population, so, how can we solve this? It turns out that the initial population gets canceled. It's not important. This is how exponential growth works. What matters is the ratio of growth, okay? So you get this P naught canceling, and you're able to solve for k. And then we're going to solve for the time when P equals 3 P naught, okay? So we know after 1 hour, you get 3/2 P naught. When will you get 3 times the population? Okay, instead of 1.5, 3 times the population. And notice here that I define T3, T sub 3, to be the time when the population triples, the initial population triples. Okay, that's just to kind of make clear here that that's what I'm solving for in this problem. So again, left-hand side is the condition that we're solving for. 3 P naught is equal to P at some time. Right-hand side is plugging in T3 into our general form. And again, the P naughts cancel. We don't need to know them initially, okay, which could confuse some people who try to just work with this without equating the two conditions and getting that cancellation. And notice then when we solve this, so we straightforwardly, we have k now, we're solving for T3, we get this equation, and plugging in k that we found above, which is per hour, okay, then we get 2.71 hours. So notice something important here about exponential growth. After 1 hour, the population grows by 0.5 P naught. And so naively, you may think that in order to add another 1.5 P naught of the population, you would need 3 more hours, right? But it turns out that we're undergoing exponential growth. So the final time is not 4 hours, as we might have thought by naively extrapolating the first 1 hour to in getting 0.5. And so then you'll have 1.5. And if you need another 1.5, you might think, okay, every hour I get 0.5 population. So I need 3 more of those to add another 1.5. And the sum then would be 3 times the initial population. But that's not how it works. We're not getting 4 hours. We're getting 2.71 hours. And why is that? Well, the rate of growth is not constant. The error that we would be making by having this naive guess is that we're using linear growth. And here, as time goes on, the rate of growth actually increases. So it's very common when people think about interest rates and compound interest to make this mistake of thinking linearly. And here we see an example of that, and it's important to keep that in mind.